Hey robot makers, hope you're having a good day so far. So, do you want to learn how to build a brachiograph and create artworks with a robotic arm? Then this is the show for you. So let's dive straight in. My name's Kevin. Come with me as we build robots, bring them to life with code, and have a whole load of fun along the way. Okay, let me just get my workstation sorted here. Let me get over to the slides. So I've got a little video playing in the corner. It's not a video, it's actually a live stream. I can just wave my hand there to show that. This is currently drawing a picture for us. So I wanted to set this going so while we're talking about this, you can see it kind of in action in real time. Okay, so yes, this is all about how to build the cheapest robot arm out there. It's ridiculously fun and really easy to do. So let's go and have a look at how we can do this, shall we? So yes, this is a brachiograph. Now brachiograph is from the Greek brachio, which means arm, and graph, which means writer. Oops, I thought I'd turn that down there. So yes, kind of a joining of two words there. And yes, it's a very simple and affordable open source drawing robot. This is what drew me to this. And it's built using really common materials and powered by a Raspberry Pi. So it's just running Python, a couple of Python scripts. And the brachiograph is from the Latin, I think it's really from the Greek, brachium for arm and graph for writing, arm, writer. So you can see it's just currently writing, drawing a little picture in the corner. So this was originally created by Daniel Procida. Daniel describes the brachiograph as the world's simplest, cheapest drawing robot, which is pretty cool. And you can actually draw, in part of the demo, we'll try that in a little bit, a picture of Daniel. Let me just find the one I did earlier. There it is. So the arm can actually draw that picture that you can see there, and this one took 25 minutes to draw, so that's why I wanted to start this particular one drawing right away. This one only takes about 20 minutes to draw. Cool. And that's actually part of the demo library. So how do we actually build this arm? I wanted to sort of show you how we would do this because it's really, really fun. Let me just get my notes up there. So what we need is a Raspberry Pi. Now any Raspberry Pi will do. So the cheapest Raspberry Pi that you can buy is the original Raspberry Pi Zero. This is what they look like. This one has the header pins. I think I soldiered these header pins on, but you can get them with the header pins attached. There's also the Raspberry Pi W, which has the Wi-Fi chip on it. You can see it's got a little silver chip. Oops, just there. That means it's got the Wi-Fi that works just as well. And if you want to buy the newer one, that's slightly more expensive. This is the Raspberry Pi 2W, so it has the larger chip on the board there. This one also has the coloured headers, which helps you identify which ones to plug things into. So the red pins on the left-hand side at the top there, they're the red pins are the power, 5 volts. That's what we need to power the servos. So we also need 3 SG90 servos. I've got a couple of them here. They're cheaper to buy in bulk, so if you buy like 10 or something like that, they probably end up being something like $1 each. So it's become a little baggie like this, and they are called an SG90. They kind of look like this. So these are the really, really cheap ones. They have these plastic gears and plastic servo horn, and they have the usual kind of three wires that come out of them. We also need some DuPont cables. I'll just put that back over there. So what we need is 2 different types of DuPont cables. There's the male to male, and there's the male to female. Male has a little pointy bits on, the female ones have little in bits on them. So what we need is, these are the ones that are going to go onto the header pin. So we need 5 of these, 2 for power and 3 for the actual signals, and then we need another 6 of these male to male ones, so that we can connect them up to the servo header pins, and we'll have a look at how to wire them up in a minute. We also need some clothes pegs. So I think we bought this pack of 36 wooden pegs for about £1, about $1. They weren't very expensive. And you want this kind of variety that's got the spring in it, because that's going to be the thing that grabs hold of our pencil or our pen. And we're going to hot glue this to the next component we need, which is some popsicle sticks. Or in the UK we call these lolly sticks, or craft sticks. So we bought, I think a pack of these, there's about 50 of them for £1, for about $1, for about €1. So yeah, you can get all kinds of different colours there. And we just need 2 of those. So wooden ones are the best ones, are easiest to work with. And you also need a hot glue gun. So I have a hot glue. I've got a regular kind of, this one is a Pritt stick, which is like a glue pen. It's that kind of white PVA glue. And that's to stick the paper to the board. And we also need some, grab this, foam core board. So I've got an A4 side of foam core. So this is a little sample of foam core. It's kind of like cardboard with like a little spongy piece of foam in the middle. Quite cheap to buy. It tends to come in like enormous sheets. So I cut this one down to sort of A4 sized, and we're going to sort of stick that glue pen, this sheet to it, which I'll show you how to download this in a second as well. And I have a hot glue gun as well. So these are quite cheap to get hold of. They're fantastic for doing all kinds of crafty type projects. So I've just got this little one that plugs in and uses these little glue sticks. So that's what I've used to construct the entire brachiograph. And the other thing you need as well is some pens or a pencil. And I'm currently using a Sharpie on this this one that's working down here. So this is just like a black Sharpie. And I've also got some what they call Stadler fine liners. These work quite nice as well if you want that more fine grain effect on the artwork that you produce. And we also need a little breadboard. So you can either go for one of these regular kind of breadboards, or like you can see on screen there, the mini breadboard. And that's simply just so that we can connect the power to the servos, because the problem is with our Raspberry Pi has two 5-volt leads, but we actually need 3, so we need some way of making 2 go into 3 or 1 go into 3, so we can simply just use the breadboard to connect the power to the servo motors. So you can see on this this diagram here, we have the foam core board, which has got the grid stuck to it. We have, let's have a look on left to right, we have the Raspberry Pi itself. So I'm currently using a Raspberry Pi 3 Plus, which is the one that doesn't have the Ethernet connector on it, Ethernet connector, but it's good enough, and it doesn't have to be particularly powerful to run the scripts that we're going to be using. In the middle left there, we have the mini breadboard. You can see we've got some of these DuPont cables, which are these cables that we can use to plug into the servos and to the Raspberry Pi pin headers. We have a little shoulder motor, which is just the SG90 motor. We then have the popsicle stick. We've got the elbow motor, another popsicle stick, a clothes peg that's been hot glued to that, and the lifting motor, the pen up and down motor, which is also connected to that. We've got the pen, and we've also got some bulldog clips. These, I'm not sure if they're called bulldog clips in every country, but they're essentially these little, I'll show you this on the camera. These little clips, and these can hold the paper to the foam core board. So they've got like these little clips. These are like the original fidget spinners. You'd sit there for ages like making things out of them. So I've got a whole bunch of these, again about £1 for 20. They're quite cheap to get hold of. You could just blue tack the paper down to the foam core board if you wanted to, but I find it's best using these little clamps. They don't leave any marks on the paper, so pretty cool. You can see there, that's what the constructed brachiograph will actually look like. You can see it's working way down here as well. So there's a question from Adam there about wanting continuous rotation servos for 360 degrees. For this we don't need 360 degrees, we just need the 180. So to install the code that we want to run on our Raspberry Pi, there's just a couple of steps. I'll put them on screen here just so we can go through this. So on the Raspberry Pi, it's assuming that you've got a brand new Raspberry Pi, you've flashed it onto your SD card, you booted the Pi up, you've got a keyboard and mouse and everything attached, and a monitor, and you've been able to launch the terminal, which is that little black terminal icon on the top of the menu bar. So once you click on the terminal, you can then open up the terminal and type in the command to clone the repository. We'll do that in a second. I'll show you how to do this. It's just a simple git clone command, but that's the actual path to it. So github.com/evildmp/brachiograph. Once we've done that, we can then change into the directory that's been created for us that has all the code in it, which is Brachiograph, so CD changes directory into Brachiograph. We then need to create a virtual environment. This is a Python thing, so Python likes to have virtual environments for each project now, and it's a way of just keeping all the dependencies, all the libraries and everything sort of in sync with that particular project. So if we do Python 3 Python 3 space -m and then space venv space venv, that will create a virtual environment that's called venv. We can then activate that virtual environment by typing source and then space and then the path to venv bin activate. If you press the first letter of each of those and then tab, it should auto complete that, just to help that speed up the process of typing it in. And then we can run pip install space -r requirements.txt, and this will install all the dependencies for the project, and then we'll be ready to launch Python and start playing with our Brachiograph. So we will do that in a minute. I'll show you a bit more about that in a second. So how does this actually work then? So the Brachiograph doesn't know how to draw pictures directly. It knows how to move the arm around to a set of coordinates. And we can put a whole list of those coordinates into a JSON file, a JavaScript object notation file. So we need a program that can convert pictures into this JSON format. We have got one of those. We'll have a look at how to do that slightly later on, if I remember to do that. So the image is converted into these series of lines, also known as vectors. A vector is just a line between 2 points. So the picture gets converted into the vectors. The vectors are then stored in this JSON file, and then the Brachiograph has a library that's just called plot file that can be used to start working on that. That's exactly what's going on over here on the left-hand side, bottom left of the screen there. And we can also move the pen up and down. We'll have a look at that. That's quite a fun thing to see how that actually works. It's quite ingenious with such simple pieces of material, if you like. So how does this work? The images, like I said, are converted to lines in a similar way that a 3D printer converts a 3D model into a series of paths for the 3D printer to follow. You can see that the line drawing on the right-hand side of this slide here, that's Daniel, that's the inventor of the Brachiograph. And you can see there it's made up of like lots of little lines, and that's what the Brachiograph can see. It can read each line, and it can just move the pen and then make the pen make a mark on the paper. Now the pen and the paper, it is a little bit rough and ready, and that's part of the charm from my perspective. So if I hold up this picture here, this is a picture of, can you see who that is? Nikola Tesla. If it's kind of like a bit blurred, it kind of looks even better. But when you like get up and close, you can see it's just a series of like very squiggly, scratchy lines. And that's because when the pen that goes on the paper or the pencil, it can sometimes like make a little line as it goes up and down, because it's not going up and down perpendicular to the paper. It's kind of going in that kind of orientation. So you get these little like tick marks. Well, that's kind of the charm of the Brachiograph. It makes it look a bit more interesting. So you can see, yeah, the individual lines, that's how it will draw out the picture. So it's really, really cool. Very, very simple. Adam's saying there, you need to have an understanding of trigonometry and angles to get started. Is that in relation to how to draw these things? Because the library takes care of all of that for you, which is pretty nice. Cool. So I think that's actually finished drawing now, which is quite nice. We'll have a look at that in a second. Let me just move that out of the way. There we go. It just got a bit caught. And you can see that is Alan Turing, that picture there. So if you like what I do and you want to make more of these kinds of videos, please drop a like on this video. Drop me a comment as well if you want to tell me what kind of robot arms you're working on, if you've used one of these. If you want to build one of these yourself, and if you have, send some artwork into the Discord group, which I'll send a link to shortly. And if you've not subscribed, please subscribe. We've just hit 32,000, which is a huge milestone for me and my channel. So I'm trying to slowly go towards the 100,000 mark, but we're quite a way off there. But we're nearly a third the way there, which is quite cool. I do go live every single Sunday at 7 o'clock, so if you want to check out the channel and talk with me live, you can do that at 7 o'clock British summertime, and I do go live every single Sunday without fail. So why build one of these in the first place? So it's really, really fun to do this. I can't tell you how hypnotic it is to actually watch it slowly draw the thing out in real life, watching the pen go down and it make the little marks in the picture kind of appear before your eyes. Really easy to learn and really cheap and quick to build. So you can build this in less than an hour. It's ridiculously quick to put this together, and it's It's really quite forgiving as well. If you put this together and it's a little bit wonky, that's part of the charm of the Brachiograph. So it's supposed to be like that. Don't worry about it. And you can create all kinds of artwork, including multi-layered and multi-coloured pictures. So if you draw one picture with one pen, and then you have a different file that you can overlay, almost like layers, or exactly like layers, then you can have different coloured pens, and it can look really great. So I first saw this when I went to the Liverpool Make Fest, and Andy Piper of Forge and Craft. So Andy Piper is a friend of the channel. He was there with Heidi, and they had some of their examples for sale of work they created on a Brachiograph, and they had their Brachiograph there working away, drawing some stuff out, and it's just hypnotic to watch. So really, really great. It's fascinating to see the picture appear, and it's also a really good introduction into robotics. So if you're at school holidays and you're looking for something to do that's interesting for yourself or for the children, then this is a project you can really get up and running very, very quickly, and for like less than $15 to put the whole thing together. It's very, very cheap, and that includes the Raspberry Pi. So let's create some art. Let's have a look at how to do this, shall we? I'm just going to get my notes up on the other screen, and I can show you all about this. So let me go over to, let's go over to the overhead for a second. So here we have the Brachiograph. You can see there we've got the Raspberry Pi 3A. We have the little breadboard with all the connectors on, and that's simply providing the power, which is this black and white cable, to the first and second rows. And then we've got three other cables. One power and ground is going to each of the servo motors. And then they've got the other three cables, which are the yellow, green, and orange cables. And they're the signal cables that are going to each of the motors. So the motor I find most interesting is this pen up and down one. I'll try and get a better angle on that in a second so you can actually see what that looks like. I'll see if I can get my my phone to work on that one. It may or may not decide to work. But I should be able to get like a slightly different angle if I go to here, for example. So let me go to, if I go to this view here, then we can get kind of everything on the screen at the same time. So let me see if I've covered everything off that I wanted to talk about there. So the first thing I want to show you is I've written a course, kind of a tutorial. If you go to kevsrobots.com, go to free courses, and it's currently under a recent course, but you can also find that if you go to all courses and you go down to learn robotics pathway, then you'll find the Brachiograph one. There we go, as lesson number 5. So if we click on that, this will tell you how to build your own kind of in slow time, where to get the code from, which is this GitHub repository here. We'll do that in a second. There's the bill of materials. So I'm using a Raspberry Pi 3 Plus, but you can use any Raspberry Pi. And if you get the very original Raspberry Pi 0, these are about $5 or something. They're ridiculously cheap. So if you have one of these, it'll work fine, and it brings the cost right down for the project. You can see there the servo motors. You can typically buy like 10 for $10. They're quite cheap. The popsicle sticks you'll get more than you need there. You just need 2. I got 50 for £1 for $1. The hot glue gun, hot blue gun as it says there, hot glue gun, a clothes peg, the foam core board. You can actually use wood, or even if you have the Amazon envelopes that you get, the card on that is probably strong enough to be a base, and you need some jumper wires. Now I did 3D print a little component. It's got some blue tack in the middle there, and the idea of this is this helps us center the shoulder servo in the very middle of the board. I'll show you that in a second once we go to the overhead. I'll not construct it in real time, but I'll show you kind of the process for doing that. And then we've got the breadboard, the little mini breadboard. I think they're about $1 for wiring everything up. You can also get the DuPont cables. I think it does mention that on there. The DuPont cables, jumper wires as it calls them. It's about $5 for a pack, and you get like male to female, female to female, and female to male. And you only need just like a couple of those cables from that individual pack. So there's the assembled Brachiograph picture, and then it sort of talks you through how to get everything you need for that. If I grab this and this, so let's go over here. So I've got this this sheet that's been printed out. This is from Daniel himself. I think he produced this as a calibration sheet. So I would simply just stick this to this foam core board, just using a bit of glue stick. And then what I've then done is this little 3D printed part can just go to the very center where the 0 and the 0 align. I've designed this so that there is like a, hold this up so you can see, there's like a little crosshair line. Probably just about see it there, indentation. So it's very easy to get this exactly in the middle where it needs to be. There we go. Okay, let's get back to here. So once we've got that printed out and we've got that little spacer, you can see there the 0, 0 point is exactly in the middle of that. So we just hot glue that to the paper. The paper's been glued to the card with this. That's fine with the regular glue. You can see there it's put into place. I even drew like a little pencil line to make the alignment as good as possible. It just means that it's more likely to be better calibrated when we draw our pictures. Then the next thing we need to do is get one of these little popsicle sticks and get this servo headers. So when you buy a pack of servos, you'll get typically 3 different types of servo horn. You'll get these little singular, well, maybe this is like a double-headed one. There's a single-headed one, a double-headed one, and then one that's kind of like a cross shape. So you want this one, which is kind of the double one, and you want the popsicle stick, and you want to mark on there a point, which is about 8 millimeters. Let's go to the overhead on there so you can see this. Those little crosses I put on there with pencil are 8 centimeters apart, and roughly put them in the middle of the stick. So that's what we need to do. And what we're going to do is hot glue those little servo horns so that the very center of the servo horn is over that little point there. I'm going to hot glue that into place. And the other thing you might want to consider doing is drilling a little pilot hole through that middle section so that we can then screw the servo onto the servo horn for like really good strength, and it won't pop off while it's in the middle of drawing. Then we want to do another thing, which is get the second popsicle stick. We're going to glue a servo to one side of it and then the clothes peg to the same side, and we want the pivot point from the first popsicle stick to be 8 centimeters to the center of where the pen is going to be grabbed by the clothes peg, and that will mean that the calculations of when it does all its trigonometry will be just right. And then the third servo horn, which you can just see here, which is kind of juxtaposed to that one, this is going to have the servo spindle, the little horn at the very bottom. And if I just move to the next picture, you can probably see a better picture of that. So that's going to be flush with the top of the peg and the popsicle stick. And you can see there the pen servo horn in its down position will raise the pen off the paper. And when that moves, it'll lower it down onto the paper. That's why you get these little ticks. But it's really simple to glue these together. It's actually non-permanent. If you wanted to sort of pull things apart, the glue does come apart with a bit of force. But it's strong enough to do many, many pictures. So yes, that sheet, that calibration sheet, has been provided by Brachiograph.art, which is Daniel's website, and I put a link to that up here as well, so you can go to the base template, download that as a PDF and print it out. I think it's A4 sized. So we're actually going to be printing in A5 sheets of paper. So I've simply got some old printouts that have been printed on one side, and then I just cut them with a guillotine. So I've got some nice A5 sheets of paper to draw on. There we go. So that's the first step for putting together our brachiograph. Let's go to the next one. Then we need to wire it up. So to wire it up, there's a kind of closer view. So the top one is the 5 volts that's coming from the second pin on the Raspberry Pi pin header. And then the next pin to that, pin 3, is the ground. So the second row on here is the ground for our servo. So you can see that white and black cable coming in the right hand side there, and then we've got 1, 2, 3 there. That represents each of the 3 servo motors, because they need 5 volts of power and ground. So you can see there, that's the kind of pin out. So from the very top, you've got 2 5 volts, but we only need to use 1 because we're going to multiply that using the little breadboard. and then we've got the ground, and then we've got the 3 pins. So the first pin there, GPIO 14, is the servo for the shoulder, GPIO 15 is the elbow servo, and GPIO 18 is the pen servo. That's going to make the pen up and down. That's it. They're the only connections we need. And if you want to see that as a sort of fritzing diagram, that's what that kind of looks like. So the power is coming up. On that side I've done it kind of left and right rather than top and bottom. It's the same difference. As long as on these little breadboards, each of these 5 pins in the rows are actually connected together. So anything that's on that pin there is also connected to all the other pins on that same row. That's how they work. And you can really easily damage your Raspberry Pi if you incorrectly connect a pin while this is powered up. So what I would suggest you do is plug all the wires in while it's not powered up, and then check the wires again and then power it up, and you should be fine. So that's how we do that. And these hobby servos, just to be clear on how they work, so they've got 3 pins. The power, this is a clever design, the power is in the middle pin, so if you get this the wrong way round, you don't actually blow up your servo or your microcontroller. So the left one is ground and the right one is signal. So only the power is the one that's the kind of dangerous one. So it doesn't matter if you get it the wrong way around, you won't blow it up, it just won't work if you get it the wrong way around. You can just switch that out. And then setting up the Pi. So we looked very briefly at this. I kind of assume you know how to set up a Raspberry Pi, but you can download the Raspberry Pi imager from the Raspberry Pi website. They've got instructions on how to use it, but essentially you get your SD card, plop it into your computer, run the Raspberry Pi imager, select the correct operating system for whichever Raspberry Pi you've got. So if you've got a Raspberry Pi 2, for example, 02, you could run the 64-bit version of Raspberry Pi OS. If you've got the original Raspberry Pi 0, then it's probably the 32-bit version. It doesn't matter which one you choose, to be honest, as long as it's the right one for the board. Once you've got that written, you can then boot your Raspberry Pi up, and if you've got a keyboard and mouse and monitor, that can also help just get the thing installed. If you're clever enough to do it's headless and you know what that means, then go for that as well. Then you want to connect it to the Wi-Fi. If you're using the Raspberry Pi desktop, you've got a little icon on the top right. You can just select your local Wi-Fi connection, connect up that, put your Wi-Fi password in, check for any updates. You can either do this through the terminal, or there's now a little icon for updates, and it'll pop up and say if there's updates available. Make sure you're up to date with that. And then we want to install Python. So you can install Python through the Raspberry Pi terminal. You click on the little terminal icon on the top left, and then we can do sudo apt install python 3 space python 3-pip. Pip is the package installer for Python. And then we want to install the Brachiograph. So if we do git clone and then the actual path to the Brachiograph repository, so http www.github.com/evildmp/Brachiograph. You don't need the .git on the end, but you can include that if you wish. And then we want to create the virtual environment, and I can show you how we can do that in a second, but it's just there, python 3-m vmvm venv, which is the virtual environment. We activate the virtual environment, which means that is now the Python instance that we're using, so source venv/bin/activate. And then we want to install all the different Python libraries for this particular project. Before we do that, we want to do something that's called GPIO-D. So what this is when we want to use the GPIO pins, which is these little header pins in the real physical world of computing, we need the Raspberry Pi to be able to talk to this hardware at a very low level. So these are called GPIO pins, general purpose IO pins, and we have the Pi GPIO pins, and the D is for Daemon, which is something that runs in the background. It's like a little spirit that runs around in the back of your operating system. And super do just means run this as an administrator. Once we've got that running, the code will work in the background. If we forget to do that, it won't work. It'll just say that it can't find GPIO-D or something like that. We can then go into the Brachiograph folder. We can do pip install -r and then requirements.txt. Requirements.txt is just a text file with all the different dependencies and the version numbers of each of those that we need for this particular project. And then once we've done that, we can then run Python 3. So at that point, let me go over to my terminal. So here is a terminal I've got running already. Let me quit from here and let me show you what we've got going on. So I've done the cloning. So if I do that git clone https github.com/ evil DMP / Brachiograph. If I press return on that, that will download the Brachiograph repository onto my home folder. I'm actually already in the Brachiograph one, so this is as if we've just done that. So if I do ls, you can see on here we have all kinds of Python files. The .py files are Python, the green ones are Python files. We've got an images folder, a docs folder, some test patterns. We also have, because I've created it, the virtual environment. So to do that virtual environment, we do Python 3-m venv. That will create this little virtual environment, which we need, and then we need to activate it. I can see on here I've already activated it, so let me just deactivate it. And if I type in source, and then if I type v tab b tab a tab, it'll auto-complete that path for me, which just makes it very fast to do. And you can see here in brackets we've got the venv, which is the virtual environment. I then do the pip install -r requirements.txt. If I run that again, it'll not hurt to do that again. It's just going to check and see that they're already there. So all the files, all the dependencies, everything's already in my virtual environment ready to go. So if I now do Python 3, I'm now running Python. So if I do from Brachiograph, import, and then capital letter Brachio, and then capital letter graph, that will import the Brachiograph library that we've just installed. And now we can create a Brachiograph bg equals Brachiograph, let's just Brachiograph like that. Now when I did that, I could hear the, let me see if I can bring it on screen actually. I could hear the motor move. So let me just do camera. So I've got two of me now, and let me just change that one to be the overhead camera, which is that one there. Let me just move this, I'll move this above me. And I'll also just zoom in the camera a little bit so we can see what's going on. Okay. I'll probably just move that up a little bit so we can see what's going on. There we go. So now we're in this this environment for our Brachiograph, we can try some things out. So the first thing I want to do is let's try setting some angles. So if I do BG, which is our Brachiograph that we just created, set angles, angles not angels, and let's do 1, 1 to see what happens. Now when I press return, watch the pen there, it's going to shoot right over there. And that's because that's where that particular position is. Let's try 0, 0. And let's try 90 and 0. Oh, that's too far. Let's try like that. That's 90 there. And if we want to get the back to the default position, we can do bg.park, and this will return it back to the kind of default position there. So you can see it's going right back to the very start, nice and slowly as well. Now we also had that nice completion progress bar as well. There's a couple of other things we can do. So we can do bg.pen.down. So if I do that, you can just see that little servo horn there. If I do pen up, and you watch that, that's now up. And if I do this from the sort of side view, let's see if we can see this. I'm going to run the same command. So down, and then back up. Like so. So let's go back over to the, let's go back to that view there. There we go. So we can also do bg.status. This will tell us all the current stats of the servos. So pulse widths is how servos work. We send a certain number of pulse widths per second, and they represent a particular angle on the servo. So 1500 represents 90 degrees. Servo 1 and Servo 2 both have these, but we're representing the angle slightly differently just because of the way that the arm works. There's this thing that's called hysteresis, I think I pronounced that right, and this is the amount of correction that we can apply. So when the servo arm moves, it typically moves slightly past where we want it to, and when it moves the other direction, it'll move past as well. And we can allow for how much of that correction we want to apply. I've not applied any just yet, simply because I've not calibrated it 100%. So it works kind of good enough for the pictures that I want to create, as you can see here, but if we want it to be even more accurate, we need to apply a little bit more correction on there. And you can see there as well the wait time, that's how long it waits between doing particular instructions. So it's like a tenth of a hundredth of a second. Yeah, about a hundredth of a second. And we can also see the resolution, so 1 millimeter resolution, and the angular step is 0.1 degrees as well. So it's quite accurate in how it can move, but the actual results look quite crude just because of the way that the pen actually marks the paper. Okay, let's see what we need to look at next. So I'm going to change the paper on here, so let me just go ahead and just take off the bulldog clips, take out that sheet of paper, get a nice new sheet of paper. I'm just going to clip that back into place. The last one on there. Okay, so I've now got a nice clean sheet of paper, so we can do some tests on here now. So let's draw a bounding box. If we do bg dot box, and then we have the round and square brackets, so sorry, round brackets bounds equals, and then the square brackets. So let's do -2, 7, 2, 11, like so. And you can see there it's going to draw a box for us, and you'll see it move up and down on the pen as well. Now this box is going to be quite irregular, but we can see it's kind of a box, and this can help us with our calibration as well. You can see there it's finished, and we can also see that the pen went down and up correctly. It's not made any of the marks on the paper, which is nice. And we can do some test patterns. So let's do a bg.test underscore pattern, like so. And this is going to draw, I think it's a grid with 3 boxes in it, kind of like a noughts and crosses grid. And this again will show us just how accurate that is. Now, given this is like popsicle sticks, it's quite impressive. It sort of slowly makes its way across the page there. It's going to draw another line across. Now you'll also notice that it's not square. It's not square on. The things are actually sort of at an angle, and that's because the distance between the pivot points mustn't be exactly correct, and that's, we get sort of a skewing of the angles because of that. But we can correct for all that in software. We just need to apply a bit of calibration. So I'm just going to let that finish off what it's doing. You can see it takes its time, it's nice and slow, and you get that progress bar just at the bottom there as well. That's going to do the very bottom line there as well. And then it should start doing the vertical lines as well. So I'm taking its time. If I just zoom back a little bit. Oops, drawing another line on the bottom. Didn't realise there were so many. And then it's moving to the top right of the box. So let's see how accurate it makes that. Oh no, that's the very middle, and then it's going to the very edge. There we go. Drawing that quite quickly. Oop. Just slipped off the edge of the page there a little bit. There we go. It's going to draw the next line now. So it's not bad. If you think of the calculations that are having to be taken place here, the trigonometry involved drawing a straight line with 2 pivot points. That's quite interesting how you can do that, because you actually have to correct each time, every second that you're moving, you're having to sort of correct the angle. So that's why we get that little squiggly bit. And the servo motors are not like very accurate at the end of the day. hence why you get this little wobbly line, but it's quite fun to watch this. So I have actually built two other robot arms that use a similar kind of thing. So the Pico Tico, which was a noughts and crosses playing robot, we did that quite a while ago. And there's also Buddy Junior, which is just sat behind me, which is another robot arm that we created, and there'll be more on that in the next couple of weeks as I do some videos for VM on that. Here we go. So we've nearly finished off our there we go, our test pattern. You can see that it's at almost the extremes of what it can reach. I can go for that other view there as well, just to see that. There we go. And then it's going to go back to its sort of default position. There we go. So let's have a see what else we can do. So they were all the test patterns. So what we're really interested in is drawing pictures of things. It's quite an interesting process that we go through to draw pictures. So I'm going to go back to our tutorial for a second. I'm just going to find the vector images to learn how to do this. So we need a couple of other pieces of Python libraries installed to get this to work. So we need to quit out of our Brachiograph Python. We need to do pip install opencv-python-headless, and this will install the OpenCV library. And then there's another piece of code which is already installed on the Brachiograph, which came as part of the repo, which is called line draw. So from line draw import star, and then we've got the conversion thing, so we can then convert an image into that JSON, that list of instructions. So we do image to JSON. So there's an example images of Africa. There's this drawing contours. So the drawing contours is how many times it will go over the features. So sorry, it's how many times it will draw the actual contour of the black part of the image. So the images it works on are kind of black and white monochrome. If it's not monochrome, it'll just convert it into like a grayscale image, and then into a black and white image, and then from there into something it can draw. And then there's these draw hatches. So the hatches are the sort of shading that it does, and the contours is just how it finds the edges of an image. So you can see there once, and we can tune those. So we've got a value of 2 and a value of 16 there. So draw contours goes between 2 and down to 0.5. So between 4 and 0.5. 0.5 being loads of detail and 4 being like really crude. Draw hatches, it goes from 16 to 8. 8 is like lots of detail, and you'll take quite a while. So I did do a picture. Let me find you the example pictures that I had. I did one of the Mona Lisa, and it took a very long time to do. I think it was 2 hours for it to actually draw out that picture. And the results were not great. Let me just find you this. Here you go. So that's the picture it did of the Mona Lisa. And you can see there, it's mostly just cross-hatching, and that's because I'd set the cross-hatching to like the most detailed version, like 8. And I also set the drawing contours 0.5. So you can see there it looks, I mean, if you know it's the Mona Lisa, you might be able to see the sort of side-on profile, a bit of shading under her chin and everything. But yeah, mostly it just looks a bit of a mess, to be honest. I don't think that worked out particularly well. Whereas the Alan Turing pictures, I think, came out quite well. He's sort of recognisable as Alan Turing. And what else did I do? I did one of, let's see, a famous landmark. I was thinking what would be a good thing to, something that people recognise and would know even if it was really crudely drawn. There we go. So, where's that? Where in the world could that be? Hint, I went there last month. And what else have we got? And that was the very first drawing that I did, which is Daniel Procedure, and that's the grid that it drew for me. You can see it's and it kind of draws it sideways, that kind of orientation. If we're putting it on here, kind of come out like that. You can see they look very, very similar. So yeah, so that is San Francisco. That's the Golden Gate Bridge, which I managed to drive across. Cool. So that's how we do the conversion. We simply just say image to JSON. We pass in the path to the file. It can be a JPEG file, a PNG file. It doesn't really matter. just passing the path, and then you've got those two levers. You've got the drawing contours and the drawing hatches. Now there is an extra thing you can do, which is repeat contours, and it will essentially just draw the contours twice, and that's really good for getting like a defined edge, like on a face or something like that. It'll go around it twice. Now it can take quite a while depending on what Raspberry Pi you've got to do the conversion. It has to basically work out a lot of maths to draw these lines, and depending on how many lines there are, like this Mona Lisa one, it could take it an hour just to do the calculation. Now what it will do is it will provide you an SVG file, which is a vector-based file, so you can check the output. You can actually see before you commit the time for it to draw it, does this look good? Does it look high contrast? So is there nice white areas and dark areas, rather than just lots of cross-hatching everywhere, which there was with the Mona Lisa. And then we use the vectorizer if we want to then convert the lines into a format to a shell script, but we don't want to do that on this particular one. It will output the JSON file, and then we can simply just do plot file and then pass in the JSON things, and we can see how that works. So if I just run that one that we did at the very start of the show, and I'll just leave that one running, you'll be able to see how that works. So let's go back over to the terminal, and if I just cursor up, I'll just find all the ones I did before. So there we go. So plot underscore file images Alan Turing.json. That will draw us the Alan Turing picture. So let's just get a nice new piece of paper on here. So I'd see this more as like an artist tool rather than as a drawing robot. You can tell the robot, using those different dials and levers, how much detail you want, and depending on which you choose, kind of defines how good the output is going to be. So it's kind of a bit hit and miss. Right, so there we go. So I'm going to do the Alan Turing one. I'm going to hit return, and we're going to see the pen sort of come into life there. So it's just going to get into the very first position. It's also really quiet. If I move the microphone over, see if you can hear the actual servos. They are really quiet. Really, really quiet. Barely audible. So that's another good thing about this drawing robot. It's really quiet. Doesn't make a lot of noise. And you can see that. So this one's going to take about 20 minutes for it to draw. I think it's just about shy of 19 minutes. And you can see there that we'll get this progress as it's just reading in the next block of lines and processing them. And you can see, to begin with, it just looks like a load of random lines. Then after a while, you'll start to sort of see it take shape. So I think, if I hold this one up here, this is what it'll be drawing at the moment. So you can probably just make out that sort of top section just there where his neck is, the nape of his neck. And you'll start to see, I think it does some of his eyes next. You'll see them appear as well. Cool. So let me just see if there's anything else. I think that's everything else I wanted to cover off there. So I'm going to go back to the slides, but I'll have this, I'll return to this and you can see how it's going. Cool. In fact, I'll just leave it down there so you can see it drawing away. Cool. So if you want to get some merch and help support the channel, you can get yourself one of these amazing Robot Maker hats. Quite a few people have bought these. They clearly know that these are the thing to wear this summer. So should give up the day job and just become a salesperson, shouldn't I? Go to kezrobots.com/merch if you buy one of those. And if you want to check out our Discord group, and if you build one of these, I want to see pictures that you've made in our Discord server. So yeah, just drop in the what I've made channel, and I'll have a look at those because I want to see what people come up with and what ideas they have. Andy Piper from Forge and Craft has some amazing examples. I think you can even buy the ones that he's made on the website. He's built like a really professional grade brachiograph, but the one he brought to the show was basically what we have on screen now. If you want to follow me on social media, I'm all on the social medias as well. So on Threads, I'm at Kevin McAleer at threads.net. On TikTok, I'm at Kevin McAleer 6. On Instagram, I'm at Kevin McAleer. On X, I'm at KevsMac. On Mastodon, I'm at KevsMac at mastodon.social. I was interested to know as well, Andy Piper is actually a Mastodon developer. He does something to do with Mastodon, so that's pretty cool. And I'm also on Blue Sky, so if you go to kevsmac@bsky.social, I'm on there too. So follow me on all those places, say hi, and you'll get some behind the scenes things, some teasers and all the rest of it. And if you want to join me, you get your names in the end credits. You can do that by going to kevsrobots.com/coffee. If you're watching this live, you can do a super chat, and that will pop up on screen. Let me make sure we've got those enabled. So let me just click on that button there. There we go. If you're watching this on replay, you can do a super thanks. There's a little thanks button that appears after you're subscribed, and you can click on that and donate kind of for the price of a coffee as a one-off thing. And if you want to go further than that and pay for a coffee every month, you can do that by joining the YouTube membership program, or if you prefer the Buy Me a Coffee membership program, they're both the same kind of price. It's very, very cheap, but it does help support the channel. It means I can buy paper and pegs and things to build more robots with, and servos and whatnot. Cool. So let's have a quick shout out to our supporter, shall we? So here we have on Ian bought me 2 coffees. Thank you, Ian. I really do appreciate that. It always brightens my day when I see somebody's bought you a coffee. I'm like, oh, how kind, how generous. On the Buy Me a Coffee membership side, we have Shemi, we've got Alvaro, we have Marie, Jeff, we have Steve, we have Diane Corti, Marlene, and Tom. And on the YouTube membership side, which side are we? That side. We have is it Fafasin, we have Littleback, we've got Ford, we've got Alvaro, we have Paul, Johnny, Dale from Hybrid Robotics, we've got Hans from Chairlights, we have Stephen, we have Jonathan, we have John Paul, we have Alistair, Cassie, Tinkering Rocks, JDM, Johnny Bates, we have Michael, and of course we have Tom as well. So thank you so much for supporting the channel. It means so much to me that you follow me and subscribe, and you support the channel as well. Cool. Let me have a quick check and see anything else I wanted to cover off. Nope, so that's everything I have for you today. So if I go over here, YouTube will be suggesting a video over here. Please click on that one. It really helps the channel as well if you sort of binge watch my content. So definitely check out this video. It thinks you'll like it. And I shall see you next time.